Hi, everyone. My name is Emily Mattis, and I am the AIM host for this particular breakout session today. I promise I won't be on the whole time, but as you guys come into the session, we still have about 10 minutes left. So if you want to visit some of our expo booths, do some networking, this would be a really great time to do so. But sit back and relax. We'll get started around 10. The other thing that I would say is only the speakers will be sharing their video and audio, so you can just sit back and relax and enjoy the presentation. You don't have to worry about sharing anything. You can just sort of enjoy the presentation. I'll be monitoring the chat, so if you have questions, please feel free to put them in there, and I will make sure that they get recognized, or we can connect you with our speakers as well.
Hi, Emily, can you hear me?
Yeah, I can hear you. Hi, Madison.
Great. Well, I'll probably hang out here on mute while people join, and yeah, we can plan to get started at 10.
Sounds good.
Awesome.
Good morning, everyone, and welcome to the session. My name is Emily Madison. I'm going to be the AIM host for this session, and I'm going to jump off the screen as soon as everything gets started, just here in the background to make sure that everything is working in case any technical difficulties pop up during the session. Please feel free to enter questions or converse in the chat. I know it's a little bit different since we are all virtual. Normally we would have sort of that normal conversation happening if we were all in a room together. But please feel free to ask questions or talk amongst yourselves, share information and ideas in the chat as we move about the session today.
Thanks, Amy, and I'll give everyone another minute or so to get joined before we get started. I'm also going to be co-presenting with my colleague Tyler Bybee, and it looks like he's joining right now. So, like I said, we'll give everyone about another minute, and then we will dive in.
If you guys need anything, I'll be here. I just won't be on the screen, but just say the word and I can pop back in or troubleshoot whatever I need to. That's what I'm here for. I'm gonna hop off now so you don't have to look at me anymore.
Sounds good. Can you hear me?
Yes, I
Okay,
can.
great.
Okay, awesome. Well, thank you so much, Emily. We're super excited to be a part of Infotech again this year. We really appreciate the conversations we're able to have with other tech professionals at this forum. So today we are going to talk about machine learning. So let's see if I can, there we go. So we want to give you all a practical understanding of really how it works and also how you can get it started at your organization today if you haven't. And if you're trying to figure out how to get it started, we really want to make sure that you have practical ways to approach it so that way you can get business value from it very quickly. So you might be in a few different camps. You might feel like you don't really know what machine learning is, but everyone's talking about it. We can help you there. You also might be really excited about it and are trying to push it forward at your organization. I think this will give you some good ways to maybe approach it and bring it to either leadership at your organization or share it amongst your colleagues. Or you might already be doing machine learning at your company and maybe you found some really great insights and you are developing models, but maybe you're struggling on getting people to really buy in and push it into deployment and start using it in production. So I think you'll learn some ways to help demystify it for people who might be a little wary about machine learning still. So I think there's a lot of different things that you might be able to take from this presentation, regardless of where you are on your journey. So with that, I do want to give a little overview about who we are here at Zirous. So we are a tech consulting company. We are headquartered in West Des Moines, Iowa. We have a lot of colleagues who are based out of Omaha. We've done a lot of work in Omaha, and we really focus in and around the Midwest. So we were established in 1986. So over obviously that 35 years, tech has changed a lot, and we've really always been grounded in data. So we like to pride ourselves in how nimble we've been able to be and how we really like to anticipate what's next on the tech horizon. So we can always make sure that we are proposing custom and advanced solutions for our clients. So Tyler and I are part of our data analytics and engineering practice area, but as you can see on the screen, we have other practice areas such as cloud and infrastructure and marketing technology and integration. So we really like to think that we can come alongside of our clients and regardless of where you are on your data maturity, what part of the data lifecycle you might need assistance with, we really are that full cycle partner, and we like clients to think of us in that way. So who are we? My name is Madison Lang, and I am our Director of AI and Machine Learning.
And I'm Tyler Bybee, one of our machine learning engineers.
Yeah, so I think today we just really want to both, we'll bring you some different pieces of um, throughout this entire presentation. So to start with that, I we're going to really start with demystifying machine learning. So um, what is this buzzword that we're always constantly hearing about? And then we're going to unpack some of our methodology that we use. So, how do we look at data and make sure that we're balancing governance while also still providing sufficient access for exploration? That's what we're going to do when we look at enterprise data foundations. It's a framework that we've presented to a lot of different companies, and it's really resonated with them. So I think you'll see value in that. And then I'll turn it over to Tyler, and he'll walk through the data science process and kind of show why it's hard. And we'll discuss the skill sets that can really help advance your analytics team's success. And then finally, we really want to be able to dive into one of our use cases. We'll show you the analysis we performed and the insights we were able to uncover for an urban hospital, and they did see a 10x ROI on these insights that we were able to show them. So with that, let's go ahead and dive in without any further delay. So demystifying machine learning. So some of you might already feel comfortable with machine learning, but to level set, we really want to lay the proper conceptual foundation to really make sure everyone is on the same page before we dive into too many details. So let's first start with reviewing some definitions. Many of you have probably heard the most widely used definition of machine learning, which is it's the ability for a machine to learn without being explicitly programmed. So while this may give you like an aha moment for just a little while, when it comes to businesses actually investing and paying real dollars for a self-learning machine, they tend to come back fairly quickly with some additional questions. Maybe, so how does it learn? What is the machine that is learning? What is it learning from? So another way that it's often described is mapping a set of inputs to an output, which is also correct, but still very abstract, especially for non-technical people. Inputs and outputs doesn't really paint a really clear picture. So that's why the basis of my explanation for machine learning today is going to be based more on this definition, which is learning a function from data. So all three of these may sound very similar because they are. They're all correct, but this foundation that behind all of machine learning, all it is just a function, to me plays a much more helps plant a much more concrete understanding of what machine learning is. So a function, remember, is just being able to calculate an unknown value based on a lot of different variables. And variables, by definition, change. They're always varied and changing. So as they change, the value that is calculated based off those variables also changes. So sometimes you can just solve a function, right? In math, you learn that as long as you only have one unknown variable, you can simply solve for that unknown variable. But now you can imagine that you have a lot of different variables and you have no idea how to explicitly solve for those different variables. Well, that's this power of machine learning. All it really needs to do is look at all of the existing data and the variables that you're considering, and it can solve for all of them for you. So with that, let's dig a little deeper and get into really what this function is that machine learning can solve for you. So a lot of people's first experience with functions is back in algebra, and you probably all remember this idea of a line, and really all a line is a series of continuous points. And the first, function you're introduced to is this basic framework of y equals mx plus b. And then you learn that you can solve for these different variables once you are able to know the some of these data points on the line. So for instance, if you find the coordinates of 2 points of these lines, you know that the slope of m can be solved for based on the change in x over change in y. And then you can plug in that now known variable of the slope and solve for your intercept. And now you can use this function to solve for any point on this line. So now our resulting function is 0.25x plus 1. So to solve for any y coordinate, all you need to know is the x, and then you can take it times 0.25 and add 1, and that gives you y. But what does all of this really mean? Let's look at it in a little less theoretical way. So let's make it more concrete and think that I want to be able to predict the sale price of a house. So I want to be able to define my y variable of sale price given any value of my x variable. So you might start to think, well, what variables affect the sale price of a house? Well, one of them is square footage. We kind of know that as square footage, as houses get larger, they tend to sell for more money. So if you were given a function of y equals $10,000 times the square footage of x plus $20,000, you would be able to solve for the square footage of x. So here are some examples. A 1,000 square foot house would sell for $120,000. A 2,000 square foot house would sell for $220,000. But here's the thing, right? If we were to plot real life data of sale price of a house versus the square footage, it would look maybe something like this. And as you can see, in real life, data does not fall perfectly on a line. You now have a lot of real data points well above the line and well below the line. So if you were to use this function to predict the sale price, it's not going to have a very good score in being able to predict that sale price. So how would we be able to make this function perform better? Well, what we do is we add another variable. So we know that another variable that impacts the sale price of a house is how many bedrooms are in that house. And once again, as the number of bedrooms maybe go up, you would expect the sale price of the house to go up. So we'd be able to plot both of those variables against the sale price, and now it's in 3 dimensions, and your prediction would look something along this plane. But as you can see, once again, there's still so many data points above and well below the plane, so we're still not predicting the sale price very well. So what do? Let's add more variables. So we could also consider the number of bathrooms. So let's see what this would look like. Already we're struggling on figuring out how to conceptually picture considering 3 variables along with the sale price. So seeing in 4 dimensions. And if you've seen Interstellar, don't try to tell me that you understand that 4D cube that they reference. As humans, we really don't have a good grasp of understanding or visualizing more than 3 dimensions. And not only that, the math is now way more complicated. This isn't something that you would be able to pick up in 6th grade algebra. We also know that stopping here, if we were able to picture it, still would not really give us that great of a prediction on sale price. We haven't even started to consider what we know to be the 3 most important variables, right? Location, location, and location. So if we were actually going to be able to create a model to represent the sale price of any given home, also known as the Zillow's estimator, right? That function might end up looking something more like this. So this brings us back to that original definition of machine learning. What if this is what you were looking at and you wanted to explicitly program this function, meaning you wanted to solve for mathematically each of these variables? Let's just say it probably wouldn't be that great of use of your time. So today, a lot of businesses instead settle for what they can solve for, such as maybe looking across 3 variables to determine their most valuable customers. You've probably heard of recency, frequency, and monetary. Or maybe a workers' comp insurance company offers premium rates based solely on the number of employees at a company and what industry they're in. Those are two really very real examples that businesses tout today as analytics when we're talking with different clients. So you probably still want to understand a little bit more about how machine learning could kind of turn that on its edge and allow you to consider way more variables. So let's try to look at this really quickly, still back in 2 dimensions where we can conceptually understand it, but show you what machine learning is really doing under the hood. So here we have our x-axis and our y-axis and our data, and we want to draw a line that best represents that data. So let's pretend we couldn't explicitly solve for the perfect line. We can do it like machine learning does, which is it starts with a random guess. And after making that random guess, it gives itself a score based on how close all of the points are to that line. And then it takes another guess to improve that score. And as you can see, this second line looks a little better. This score would be higher, but let's do it again and again and again. And it's going to continue to do this until the amount of error, the amount of distance of those points to that line gets less and less and less. And then it'll stop once it gets to that best performance and that distance is no longer decreasing. So this should give you all an idea of why so much data is needed for machine learning. So remember, when you're mathematically solving for an equation, you can only have one unknown variable. So if you had a problem with 100 variables, you would require 99 data points just to mathematically solve it. But if you actually want to get to a good prediction of new incoming data, you would need multiple distinct examples for every single one of those variables. So when we're talking about thousands of variables, you need thousands of data points just to mathematically solve it. But if you want to get a model that's really performing well, you need multiples of those 1,000 variables. So let's take a math break here for a second and let's look at machine learning in a much more conceptual way that I think will maybe demystify it even more for those who might still be spinning. But it's also a great way if you do already understand all of this. This might be a great way to explain it to colleagues and just a wide range of audiences. So we like to look at machine learning models as that of a recipe. So let's say you were going to make chocolate chip cookies. Your recipe tells you what ingredients you need and in what quantities you need them to be able to make your chocolate chip cookies turn out. The correct ingredients in the correct ratios is what really would make your chocolate chip cookies taste really good. So similarly, with a model, you can think of a model as that recipe to be able to make a good prediction. So it tells you how much or what the weight of each of those ingredients, aka your variables, is needed to make your predictions. So out of a recipe, you get tasty cookies, and out of a model, you get an accurate prediction. So another way that this metaphor really works is, so say that you are always, you're always trying to make the best chocolate chip cookie recipe. And so when you make the cookies, you might realize after making it a few times some different tweaks that you can make to make it even better. So maybe you find out that your butter always needs to be soft, or you need a little extra baking soda. Similarly, with a machine learning model, the more and more data you have that you're able to train your model on, it may over time realize that the square footage of the house has less of an effect on the square footage of the house has less effect on the sale price, or the number of bathrooms actually is a little more important than originally thought. So the more times you make that cookie recipe, the better your cookies get, and the more times you use your model, retrain your model, the better your model is able to predict what you're predicting on. Now, the last way we also like to compare these two is when you go into the kitchen, you know that you want to make chocolate chip cookies. You don't go into your kitchen and just throw a bunch of ingredients in a bowl and hope that something tasty comes out. You know, you go in aiming for chocolate chip cookies. A really important distinction to make with machine learning models is you have to define what that prediction is before you go forward in trying to train train your model, even before you start to clean your data to make it in a way that you could start training that model. You have to have a business problem to solve. You have to have a question that you're asking of your data. So with that, what kind of questions can you ask of your data? There are three main types of questions you can ask of your data. The first is how many. So you're trying to predict a numerical result. This is called regression, and some examples of that might be trying to understand when will the peaks in my traffic at my website be, or how many customers am I going to expect on Black Friday, or what is the lifetime value of my customer? You're trying to predict a monetary value in that case. So that's one question you can ask is how many. You can do regression results. That's kind of the example that we looked at so far with that function example of the sale price of a house. The next type is you can look at category examples. So you might be trying to determine should something fall into this category or that category, or which decision should I make given a very specific number of options. Some examples of this might be spam detection. So as an email comes through, is it spam? Yes or no. If it's spam, we'll send it to our spam folder. If it's not, we'll send it to the inbox. Another might be fraud detection. Is this transaction fraud or not? Or is this person likely to churn? Is this person going to leave my business or not? Those are, yes or no questions, or a which question might be, which ad should I recommend to this particular customer? Or what day should I have my new product launch? All of those, you have very clear, distinct choices, and that type of machine learning is called classification. The third type is a little different. So with regression and classification, all of that data comes in and is very clearly labeled, and then you are trying to predict something that's also very clearly defined. Groupings, also known as clustering, is different because you're not specifically putting data into a really clear defined bucket. Instead, you're really looking for trends. You're trying to see what's similar and what's different. So some well-known examples of this are customer segmentation. You might be trying to take your customers and put them into different buckets, so that way you can market to them differently. Or maybe you're looking at your patients and you want to understand which ones are high risk and low risk, so that way you can better have nurses call on the highest priority patients. So all of that, you're not necessarily, putting it into really clear defined buckets, but you're trying to say, okay, are there certain aspects of my data that kind of group together that should maybe have me treat that data differently than other types of data? So that's kind of our overview of machine learning. I hope that gives everyone a little better understanding of what it is foundationally, and maybe it's given you some good examples of how you can explain it to others. So now we want to kind of transition into our enterprise data philosophy here at Zirous. So with that, we like to look at it in this 4-box framework. And like I said, I think this'll make sense if you kind of stick with me and work through it with me here. So now we understand, what machine learning is, and it's this ability to learn from your historical data and make different types of predictions for the future. So how can we set our organizations up so we can successfully use our data which is really important if we do want to be able to advance into using machine learning. Well, the biggest thing to remember is it's really important to know that not all data is the same. And so that means that not all data should really be treated the exact same or treated equally. It's also important to know what characteristics of your data need to be present in order for you to be able to use it in the different ways you want to use it. So if you want to use it in reporting, or you want to use it for machine learning, or you want your data scientists to be able to explore it further, all of those are different use cases and different ways to use your data. And depending on what you want to do with your data should really impact how you are treating and using that data within your organization. So with the wide reaching of number of formats of data that are out in the world today, many are overlooking that there still needs to be a way to standardize and define unstructured data if you want to use it in analytics. So a lot of you probably understand that. And maybe you're overwhelmed with this idea of needing to purpose your data because it is such a complex process. Or maybe you're kind of on the other side where you're hoping and praying that there's an easier way that you can just take unstructured data and use it in your enterprise without having to go through that structuring process. Well, I think this matrix will be a good crash course in how you can move your data around these 4 quadrants and understand when really defined purpose data needs to be available, and maybe when that unstructured data is still okay and valuable to your organization. So with that, we look at the business use cases that we're trying to define. We want to know which quadrant does it fall into. So we define these quadrants based on 2 axes, data and questions. And when we split each of these axes, we split it into known and unknown. So let's look at the x-axis first, known and unknown data. You can think of known data as structured, purposed, and defined data. A lot of the times this might sit in your transactional systems and be used in your reporting today, while unknown data can be thought of as unstructured data, like maybe log files, images, video, or just data that you are storing that really no one is using yet. That would be considered unknown data. On the Y, we have known questions and unknown questions. So known questions are oftentimes metrics that are reported on today. Unknown questions might be hunches or thoughts or feelings that you might have, or something you want to explore to see if there's any good insights that you can pull out of it. So if we look at where these intersect, known data and known questions, we like to consider your foundational core. This is where your standard reporting is coming out of, and it normally encompasses all of your transactional systems that really make your business run on a day-to-day basis. So as you all know, and maybe some of you are violators of this, when you get a report, a lot of the times people then come back and say, hey, can I have an extract of that data so I can do some further exploration? Maybe can you give me that data? Just dump it into Excel, send it over to me. I have a few more things that I want to explore. So that's where we're moving up into this expanding understanding and investigation quadrant. So this is known data, unknown questions. We're expanding our understanding of well-defined data. This kind of turns into that classic case, though, of maybe if you give a mouse a cookie, because that data that you extract from your transactional systems and provide probably isn't enough. And maybe they get to the point where they say, actually, can you also pull some data out of another system that I can join up with it? Or maybe even third-party data sources. Can you send me some free text or unstructured data so I can compare it and see what I can find? So now we're getting over into what we call the innovation and exploration quadrant, which is really unknown data and unknown questions. This data is not necessarily like well defined, and also we're not exactly sure what we're looking for. We're not exactly sure what questions we are asking. A lot of the times the people who are able to work with unknown data and unknown questions are fairly highly skilled employees. But we know that there can be so much value found up in this quadrant. So maybe those highly skilled individuals are able to stumble across a golden nugget of insights. So how do you convince people to use that insight, and how are you able to operationalize maybe that model or that idea based on data that's still, as we know, based on this quadrant, still widely unknown and oftentimes not completely, trusted yet? Well, we really see, and this is what we were talking about, you really need to be able to first define the question that um, that that exploration was asking and that you were able to find. And then you are going to have to go through that process of then structuring and defining that data so you can bring it down into the core system. Because when we talk about operationalizing machine learning and operationalizing analytics, you really still have to be able to get those insights and those models back to the point where your business is using it, because you need to be able to use it on incoming data. So you really do need to get it all the way back down to that core system. So as you can see, it really is a cycle. And we need to be able to move that data around through these cycles based on the use case that we're asking. So as you move from unknown questions to known questions, so as you move down, that's really where business buy-in and making sure that you understand the business use case really, really well is so important. And as you move from unknown data to known data, as you move from right to left, that's where you really want to look at making sure that you are applying governance and have governance processes in place to do so. So the next thing to think about is, based on these different zones, who is working with the data. So up in innovation and exploration, you have a lot more unknown data, those highly skilled individuals. This is where you want to be able to equip your data analysts and your data scientists. Across the middle here is your advanced users or maybe your business analysts. And that's why I was saying they're so important to be able to make sure that you have defined questions that you're asking of your data. That business understanding is super crucial to be able to operationalize insights. And then you also have your casual users. So these are your line of business users and maybe executives, right? They don't want to get too in the weeds. This is actually 90% of your users. And this is why it's so important to be able to get back down into the core systems if you want to be able to use your insights that you find. So with that, I'm going to turn it over to Tyler, and he's going to give us a little bit of an overview of the data science process, and then we're going to dive into that use case. So Tyler, I'll hand it over to you.
Thanks, Madison. So let's talk about how machine learning fits into applying data science. Machine learning automation isn't always the best solution. There are other elements of the data science process that could be applicable to your business. So first, we'll talk about the elements of the data science process. You might recognize this as the AWESOME framework. Once you've figured out a business problem that you think machine learning or data science can solve, the first step is to obtain data and clean it. This part is likely to become a pipeline in the long run, but at first it's a very manual and tedious process. And generally this takes the most time. Most people say it takes about 80% of the time of the entire data science process is obtaining and cleaning data. So once you have clean data, the next step is to explore it. This is generally statistical analysis, and it involves enhancing the data with new features or new variables like we talked about earlier. And then we have the modeling process, where we model and interpret our data. This is where machine learning comes into play. It's very experimental, or it follows the scientific process where you have a hypothesis and you confirm or fail to confirm, or deny or fail to deny a hypothesis. But really, this is a very iterative process. The whole thing involves lots of going back and forth between points and possibly having to go back to the very beginning at some points to get more data or change your hypothesis from the beginning. So what roles exist in the data science process? Well, the first one we'll cover is data engineering. This involves making data pipelines and cleaning data so that more people have access to data. Relating back to what Madison was saying, this is the process of defining your data or moving stuff from that upper right quadrant down to the lower right quadrant. But then the next element of it is data analytics. This involves lots of cleaning data for use in reports like in Power BI or some exploratory data analysis and discovering new insights. And finally, what we've been talking about for most of this talk is machine learning. This is focused on the automation of tasks using the algorithms we mentioned, and it's really about automation and yeah. So there are many parts to the data science process. It's a wide range of skills for a single person to have, which is why it's hard to find those people. But really, machine learning isn't always the best solution. We've worked with many clients who wanted to do machine learning, but the more appropriate and cost-effective solution ended up being related to data engineering or analytics. This can be seen with our next example, how we gave over 10 times ROI for a project that lasted just a few weeks. So for a little background on our client, we were working with an urban hospital. Because of their location within a city, they serve a substantial Medicaid population, and their emergency room sees north of 24,000 visits each year. We initially met with them to give some education around advanced analytics and machine learning to help them understand the value they can have and the types of business problems that can be solved. That got them thinking, and we then had the opportunity to walk them through a use case prioritization workshop to help understand what potential business problems and solutions could lead to the biggest impact overall for the hospital. As you'll see, the hospital's urban characteristics played a role in determining the most advantageous use case to tackle. The use case that bubbled to the surface was around analyzing usage of their emergency department. That was because in August 2018, new state laws and policies were put into effect that allowed for privatized insurance companies who were covering the state's Medicaid population to no longer fully reimburse the services provided by the hospital's emergency department if the diagnosis for that ED visit turned out to be a diagnosis that was not considered an emergency. These services could see reduction in reimbursement by up to 50%, and because these were Medicaid patients, the difference in costs were not transferred to the patient's responsibility. Instead, the hospital had to write off the reduced payments as lost revenue. As you can guess, especially for hospitals serving a substantial Medicaid population, this could get costly fast. A year after these changes took effect, the hospital wanted to quantify the impact they were having on their bottom line and determine if they could identify ways to minimize the bleeding through the analysis of the emergency room data. So the hospital gave us anonymized emergency room data from 2019 with diagnosis codes, medical complaints, and other related information. Of the 24,000 unique visits to the ED that year, we wanted to understand how many were for non-emergent reasons and what determines if a visit is treated as emergent versus non-emergent. For a little more background, the same officials governing the legislation of Medicaid patient reimbursements also established a comprehensive list of appropriate emergent and non-emergent diagnosis codes. If the primary or first listed diagnosis for a particular visit is on the approved list of emergent diagnoses, then the entire visit and all of the services and procedures tied to it are classified as part of an emergent visit and are therefore reimbursable in full. If the primary diagnosis is non-emergent, then all services for that visit are reimbursed at a lower rate. Of the 24,000 visits to the hospital's ED in 2019, 44% or 10,700 were designated as non-emergent. What we were really interested in, though, was how this affected the Medicaid population, because that's where insurance companies are able to lower reimbursement rates to the hospital. Of the 10,700 non-emergent visits, almost 5,600 of them were billed to Medicaid insurance providers. So for the breadth of this project and how we can really save the hospital money is by focusing on these 5,600 visits, because these are patients on Medicaid who are in the emergency room for non-emergent reasons. To give you an idea of how big of a potential problem this is, the hospital told us that insurance companies could reduce the reimbursement on these visits by up to 50%. So if we assume that for these 5,600 cases, the hospital is getting reimbursed half, we can calculate that they basically have to write off $2.02 million on these cases, which we'll explain in more depth in a bit. So we looked at these 5,600 non-emergent Medicaid visits when we did our initial assessment, and we found that many of these have at least one diagnosis that was emergent. The team we were working with at the hospital confirmed that only the first listed diagnosis was used in determining if a visit was considered emergent or not. Here are a couple of hypothetical examples of what we mean by this. So with visit 56, the primary diagnosis is emergent, and thus the visit is reimbursed at the highest rate. But in visit 93, the primary diagnosis is non-emergent, so the whole visit would be reimbursed at a partial rate. But what we found in our analysis was that there were many instances like visit 42, where there were diagnoses that were emergent, but none of them were the primary diagnosis, resulting in the visit being classified as non-emergent and the hospital being reimbursed at a lower rate. We went back to the team and asked if this was something they would expect to happen. They told us that they've instructed their billers to list emergent diagnoses first, but that doesn't always happen for various reasons. They wanted to know how much this was costing them, specifically when the second listed diagnosis was emergent, but the primary was not. Well, what we found was that 1,424 of them had an emergent diagnosis as the second listed diagnosis, 25% of all non-emergent Medicaid cases. So what does this mean? We wanted a better idea of what was happening in these cases. So here's an example of a patient going to the emergency room, complaining of chest pain, and here's what she was diagnosed with. The first diagnosis listed was not emergent, and that's just other specified diseases and conditions complicating pregnancy. So what we have is a pregnant woman who went to the emergency room primarily for reasons that are not deemed an emergency according to the new regulation. So that means right away that this whole visit is classified as non-emergent and will be reimbursed at a lower rate. However, if we look at the rest of the diagnoses assigned, we can see the second diagnosis is chest pain, which is emergent, and then a few other emergent diagnoses like right upper quadrant pain and epigastric pain. And finally, in row 8, we see that she was suffering from carbon monoxide poisoning. So this is a really good example of the type of situation that would be valuable for them to review in a real-time dashboard. So getting back to some of the dollar amounts we talked about earlier, here we can see if we look at Medicaid patients visiting the ER with emergent diagnoses in the first row, the average amount charged to Medicaid is $2,500. And the average amount paid by Medicaid is about $750, which works out to a 29.7% reimbursement rate. But then if we look at all 5,600 non-emergent cases in the next row, we can see that the average amount charged is less at about $1,700. However, we also see they are reimbursed just $360 out of that $1,700, which works out to an effective reimbursement rate of 21.1%, much lower than for emergent visits. If we take this $361, which is about half of what they used to be getting reimbursed, we can multiply that by the 5,600 non-emergent visits, which works out to the $2.02 million we spoke about earlier that the hospital just has to write off. So now, what's really interesting, looking at the third row, there are 1,424 cases in which the second listed diagnosis is emergent, not cases where there is an emergent diagnosis somewhere, but only in the second position. These have a slightly higher charged amount than actual emergent cases at $2,600, but they have a lower reimbursement amount at $520, which means the effective reimbursement rate ends up being even lower at 19.8%, as you can see in the bottom right. So it ends up being that in cases that actually should be emergent, they are getting significantly less reimbursement than they should be. So what we did was we upgraded the reimbursement rate from 19.8 to 29.7%. That would increase the reimbursement from $520 to $780, which is a difference of $260. We can then take that 260 times 1,424 patients. We end up with over $370,000 of revenue they should be getting and they could be getting back. When we presented these findings to the hospital, they couldn't believe how much money was being left on the table and found our analysis to be sound. Obviously, assuming you could switch the primary and secondary diagnosis on all 1,400 of those visits and appealing them isn't really realistic, but they said most of the time they could easily be switched in the future. They saw this as not only a case of additional revenue, but also a chance to work with billers to place the emergent code as the primary code where possible. Which is why a lot of our recommendations were to help them implement systems to do this more proactively rather than having to appeal previously submitted claims.
So yeah,
In summary,
so in summary, I know we are running out of time, so we just wanted to thank everyone so much for tuning in. I know I do see one question asking if we use R or Python. We use both R or Python. We have different analysts who are able to align with whatever our clients use. So we are kind of agnostic in that sense. But we also help a lot of clients bring on no-code analytics or low-code analytics platforms as well. So even if you don't have R or Python programmers, we really like to still see how we can help you do advanced analytics. So like I mentioned, the first part of our presentation was all that machine learning primer, and we have a whole presentation called Machine Learning and Muffins that not only gets into that machine learning overview, but also some best practices to make sure that if you do have an analytics center of excellence, or you're trying to make sure that everyone in your organization can use machine learning and advanced analytics, we have that whole presentation. We normally bring breakfast on site to our clients, but with COVID, we are happy to do that remotely. So if you think that type of education would be helpful for your organization, please feel free to reach out. And then that use case that we just talked about was part of our Spark engagement. So if you want to go to zirous.com/spark, you can see some more information on how to get that type of quick start and quick win analytics project at your organization. So with that, if there are any more questions, please do not hesitate to reach out to myself or Tyler. Our information is up on the screen. If you have any more that you want to send through the chat, myself, Tyler, and Emily can monitor that as well. But with that, we just want to thank everyone so much again for attending. Reach out with any questions. And yeah, have a good rest of the day and enjoy the rest of the sessions.
Thank you, everyone.
Thank you, Tyler and Madison. That was an excellent presentation. I put in the chat a link to a survey for you to complete to give us some feedback on the session. Please take some time before the next breakout sessions begin to complete that for us. The feedback is really helpful in making sure that we are giving you guys the most relevant information that you're looking for when you come to these conferences. And I'm sure that Tyler and Madison would appreciate hearing feedback about their excellent presentation today. And with that in mind, the next set of sessions will begin at 11 a.m. So feel free to get up and move around, head over to the ESPA booth to do some networking, and we will see you in our next set of sessions at 11 a.m.
Great. Thanks, Emily. Thanks, everyone.